Why isn't this set of rational numbers enough? At first glance, it would appear that the ordered field of rational numbers would be sufficient to solve all real-world problems. However, a long time ago, a group of people called the Pythagoreans showed that this is not the case. The problem was first discovered when applying the now well-known Pythagorean theorem. The Pythagorean theorem says, in a right triangle with legs of lengths a and b and a hypotenuse of length c, c squared is equal to a squared plus b squared. The picture to the right here shows a right triangle. The vertical and horizontal segments, labeled a and b respectively, are called the legs of the right triangle. And the side opposite the right angle, labeled c, is called the hypotenuse of the right triangle. Let's look at an example. Consider a right triangle with legs of lengths a equal 3 and b equal 4. By the Pythagorean theorem, we have c squared equals 3 squared plus 4 squared equals 9 plus 16 equals 25. So c is equal to 5. That is, the hypotenuse of this right triangle has length 5. Another example. Consider a right triangle with a leg of length a equals 5 and a hypotenuse of length c equals 13. By the Pythagorean theorem, we have 5 squared plus b squared equals 13 squared. So 25 plus b squared is equal to 169. Therefore, b squared is equal to 169 minus 25, which is 144. And so b is equal to 12. Let's try an exercise. Let a and b be the lengths of the legs of a right triangle, and let c be the length of the hypotenuse of the right triangle. Find the third side length of the triangle given the other two. Now's a good time to pause the video, try this exercise yourself, and then resume the video to check your answers against mine. A equals 7, b equals 24. So we have c squared is equal to 7 squared plus 24 squared, which is 49 plus 576, or 625. So c is 25. A equals 12 and c equals 15. 15 squared is equal to 12 squared plus b squared. So 225 is equal to 144 plus b squared. Therefore, b squared is 225 minus 144, which is 81. So b is equal to 9. There are many ways to verify that the Pythagorean theorem is true. Here, I will provide a simple geometric argument. The following two area formulas will be useful. The area of a square with side length s is area equals side squared, or s squared. The area of a triangle with base b and height h is area equals 1/2 b times h, or 1/2 base times height. In this triangle, pictured to the right here, the base is b and the height is a. So the area is 1/2 b times a, or equivalently 1/2 a times b. Let's now go ahead and verify the Pythagorean theorem. We draw two squares, each of side length a plus b, by rearranging 4 copies of the given triangle in 2 different ways. Okay, here we have pictures of these 2 squares with the triangles inside rearranged in 2 different ways. The area of the square on the left is 4 times 1/2 ab plus a squared plus b squared. To see this, remember that the area of one of these triangles is 1/2 ab, and there are 4 of them. And then there's also a little square here of side length a, so it has area a squared, and the bigger square has area b squared. This simplifies to 2ab plus a squared plus b squared. The area of the square on the right is 4 times 1/2 ab plus c squared. Okay, again, we have 4 of these triangles, each with area 1/2 ab, and then we have a square of area c squared. That simplifies to 2ab plus c squared. Since the areas of both squares of side length a plus b are equal, we have that 2ab plus a squared plus b squared equals 2ab plus c squared. Canceling 2ab from each side of this equation yields a squared plus b squared equals c squared, which is exactly what the Pythagorean theorem says. Question: in a right triangle where both legs have length 1, what is the length of the hypotenuse? By the Pythagorean theorem, c squared is equal to 1 squared plus 1 squared, which is 1 plus 1, or 2. So the length of the hypotenuse is a number whose square is 2. Is there such a number? Rational number fact 1. There does not exist a rational number q such that q squared is equal to 2. I leave the verification of rational number fact 1 as an exercise.